Hello, welcome to the straight asymptotes of the graph lecture. Today I will discuss how to come up with the equation of the line called the asymptote for the given function f of x using the calculus approach. And the reason my presentation is that I came across through the YouTube postings, and there are so many clips there where people discuss the same way of calculating the equation of the asymptote for only rational functions using only two polynomials for which their degrees differ by 1. So you can see there are so many restrictions in this approach. For example, if your numerator polynomial has a degree of 4, your denominator polynomial has a degree of 3, then you're all using the long division, the vertical division. As the result of that, you have a linear function, and you say, and this will be an equation of my asymptote, which is correct, but this is a very weak approach. Why? Because, as you remember, I discussed different classes of elementary functions. What if, for example, you have an exponential function or a logarithmic function? Then your vertical, your long division won't help in this case. That's why I would like to consider the most general case, which is called the calculus approach involving the limits. The word asymptote comes from the Greek, which means not falling together. A stands for the negation, syn stands for sum up, collapsing, falling. Totas stands for total. Asymptote, not falling together. Yes, the asymptote is the line such that the distance between that line and the graph of your function f of s, the distance always contracts approaching to 0 when your input independent variable is approaching to either plus infinity or minus infinity, or it's equal to a fixed constant value and the distance is contracting. So in the case when the input variable is equal to a constant value and your function is defined in at least one of the half neighborhoods of that constant value, we will have a vertical asymptote. That's the first kind of the vertical of the asymptotes we distinguish are the vertical asymptotes. So in this case, again, my function has to be defined in at least one half neighborhood of the given fixed value of x, could be defined in both half neighborhoods. X is equal to a constant a, then the vertical line x is equal to a is a vertical line in the two-dimensional space. This line will be called an asymptote of the given function f of x if the limit of f of x when x is approaching a plus, a from the right, from the larger values, it's equal to either plus or minus infinity. Or the limit of your function when a is approaching to a minus from the left, from the lower values of a, that limit is also equal to either plus or minus infinity, and we have a vertical asymptote. In the case, if your independent x variable is approaching to either plus or minus infinity and the distance between the graph and the asymptote contracts, your asymptote will have an inclination, some angle, some slope, and that's the second kind of the asymptotes. They call the slant or oblique asymptotes. And as the particular case, they may have a horizontal zero slope, they will be called horizontal asymptotes. So in this case, in the case of the oblique asymptote or horizontal asymptote, your function has to be defined for big enough x values, plus or minus infinity, first condition, and the second condition, the distance between your function and the asymptote and the graph contracts to 0 when x is approaching either plus or minus infinity. The asymptote is like a mirage. You're kind of getting closer to, you see it, it's here. You're trying to get closer to it, but you cannot catch it. yes, your graph is approaching to the asymptote, but never touching it. So the distance always contracts to 0. Let's just look at the general picture. F of x is the curved line, that's our graph, and the straight line, the linear function, y is equal to x plus b, that is my asymptote. So I'll be looking my asymptote in the form of the linear slope intercept form, where I need to find those two parameters, the slope and the intercept. Those two parameters needs to be defined. The asymptote in general has the angle of alpha between the direction of the line and the positive direction of x. And the second condition, I need to look at the distance. The distance between my graph and the asymptote straight line, that is, we know that's the shortest segment which has a perpendicular direction for the point on the graph. So the distance between the graph and the asymptote will be a segment AB or BA segment. That's my distance. And also AC, that's the difference between the points on the asymptote and the point on the graph. That distance is very easy to calculate. And the triangle ABC is the right triangle, because by the definition that's the distance. It's a perpendicular direction to the asymptote. ABC is the right triangle, and moreover, the angle BAC is equal to the angle of my asymptote, alpha. Why? Because we have pairwise perpendicular sides here, and we all remember from the geometry, for the pairwise perpendicular sides, the angle between them is the same, which is what? AB is perpendicular to the direction asymptote, and AC is a perpendicular to the direction to the x-axis, which means that the angles between those pairs are the same. This is alpha, tangent alpha, that's the slope of the line. The tangent is alpha is equal to A, the slope, that's the coefficient of the slope. And BAC is also equal to the same alpha angle. So ABC is the right triangle, which means that the distance AB from this right triangle is just equal to AC, the hypotenuse, multiplied by the cosine alpha. So AC hypotenuse multiplied by the cosine alpha, that's my distance AB, and it's equal to, I can rewrite cosine alpha as multi-level fraction this way, and the distance AC, easy to calculate. That's the point on the asymptote AX plus B minus f of x plus b. Yeah. That's the distance. X plus b minus f of x gives me AC, distance AC. And it contracts to 0 when x goes to either plus or minus infinity. That distance contracts to 0. Now let's look at the one over cosine. You remember, if you bring it under the square root, it will be 1 over cosine squared. 1 is cosine squared alpha plus sine squared alpha over cosine squared alpha, which is 1 plus tangent squared alpha under the square root. So we actually have here that my AB distance is equal to my numerator AX minus f of x plus b over the square root 1 plus tangent squared alpha. That's 1 over cosine. We know this formula from the trigonometry. And again, this value is positive, always positive, more than 0. And moreover, it's a constant value. Yeah? Alpha does not change. When your x changes, we'll consider the limits. X changes. Alpha, that's the angle of your asymptote. It stays fixed, now it changes. So it's a constant positive value. It's actually 1 plus a squared also. Yeah. Positive constant value, which means it does not affect the contraction of your AB value, which means that your numerator contracts to 0. Contracts to 0, which means that your numerator, the limit of my numerator ax minus f of x plus b is equal to 0 when x goes to either plus or minus infinity. Yeah, that is the condition which tells me that my actually AC contracts to 0. Yeah, that's the difference of AC. That's AC. And that's actually true. When the distance AB between the graph and the asymptote contracts, so does AC. So we just need to consider the limit of AC contracting to 0. And from here, it's easy to tell, and we know B is a constant value. That is the intercept by the design. It's a constant value. I can pull it outside of the limit. Will be just B, and we can move my limit to the right by flipping all the signs. And finally, I will get a formula for my intercept. B will be equal to the limit. Now, f of x with the plus sign minus ax. When x goes to either plus or minus infinity, I will call it formula 1. That is the formula for the intercept. And I still need to find A, the slope. Let's look at this formula carefully, try to separate slope. I'm trying to find the value for the slope. So what if I factor x out? I can just write it as a limit. X goes to either plus or minus infinity. X out, and here f of x over x minus A. So if I consider that limit, and it's actually equal to B, it's equal to my intercept, B. Now, A separated here. I can divide both parts by x now. X is a non-zero value. By this limit, it's approaching plus or minus infinity, non-zero value. So I can divide both parts by that value. And I will get a limit of f of x over x minus a when x is approaching plus or minus infinity. It's equal to b over x. And again, by the design, b is a constant value, and x unbounded, growing infinitely, which means that the limit will be equal to 0. We prove that, you know that. So from here, I can find my A is a constant. We can pull it outside of the limit with the minus sign, minus A. Move the limit to the right, also with the minus sign. Both minuses will reduce the equation, and finally, I will get the formula for my slope, which is A will be equal to the limit of f of x over x when x goes to either plus or minus infinity. And we just found formula number 2 for the slope of my, hopefully, asymptote line. So we just need to consider those two limits. And again, the asymptote exists only when those two limits are defined at the same time. So only if 1 and 2 exist. That's very important, very important. If both limits exist, then we have a slant asymptote. Then we have a slant asymptote. Yeah, there are many cases sometimes when only one of those limits exists. Let's say b is equal to some finite constant and a is, then in this case we do not have a slant asymptote, or vice versa. So it's important condition. Two limits have to be defined only if both exist. We have a slant asymptote. So that's a calculus approach. In general, this is how we calculate those two parameters of my asymptote line. Let's just look at a simple example. I will demonstrate this general calculus approach. Given function f of x is equal to x ln 1 plus 1 over x value. Let's find all the asymptotes of this given graph. And again, where is the long division? Where is the vertical division? It won't help you in this case because it's defined only for the polynomials. And we have a logarithmic function here. That's why I'm using calculus, which is the most correct way. First of all, vertical asymptote. Yeah. We need to look at the domain. Yeah. The domain of this function, you remember, the value under the logarithm is always positive. So everything under the log should be more than 0. X is outside of the log. So what is it? 1 plus 1 over x is positive. Combined together, so it will be x plus 1 over x positive. So my fraction is more than 0. One is my fraction is positive when both numerator and the denominator have the same sign. Either both are positive or both are negative. So this is what we write: x plus 1 more than 0, x more than 0. It's a system, or x plus 1 less than 0, x less than 0 system. And the result of that intersection here, and I need to combine, take the union of those, and my domain will be x from minus infinity to minus 1, union 0 to plus infinity. That is my domain. So careful, we have the border points here that are not included, they are excluded, they are not in the domain. Actually, those are constant values, and they will be probably the candidates for the vertical asymptotes. Yeah, so let's write the candidates. The candidates are x is equal to minus 1 and x is equal to 0. Let's just research those two fixed constant values for the input variable x. For example, minus 1, and let's just follow those limits. So I need to consider the limit of my f of x when x goes to minus 1 minus. Yeah, x goes to minus 1 minus. Yeah, I can approach to minus 1 only from the left, from my domain, not from the right. You can see that, yeah? From this side. And my f of x is x by ln 1 plus 1 over x. It's really quick. If we plug minus 1 in there, 1 or minus 1 is minus 1. 1 minus 1 is 0. So actually, you'll be approaching to 0 from the positive side, because 1 over minus 1 approaching from the left will give you minus 0.999. You will be approaching to minus 1 from the right. And when you add 1 to it, you will be approaching to 0 from the right. Exactly, that's in the domain of log. So the result of that value, log of that value, will go to minus infinity. And this goes to minus 1. So minus 1 by minus infinity actually goes to plus infinity. Yeah, your limit goes to plus infinity. It looks like this condition holds. This is one of the conditions. Have neighborhood of the point minus 1, and the limit is equal to either plus or minus infinity. It's actually plus infinity in this case. And again, the log of this value will go to minus infinity, and this approaches to -1. So all the product of all minus by minus negatives will give you plus infinity. Actually, yes, that's a vertical asymptote. It's a vertical asymptote. Now, let's look at another candidate, x minus 1. Second candidate would be a limit of my function x ln 1 plus 1 over x. When x goes to 0 plus now, I can approach to 0 from the right, from the domain, which is 0 plus. That's what it means. It's equal to, really quick, if you plug 0 in here, 1, 0 is infinity, log of infinity goes to infinity, and this is 0. So it's 0 by infinity indeterminate form. And the L'Hopital's rule will help us to resolve it in this case. Yeah. First of all, let me rewrite it this way so I can apply my L'Hopital's as the limit of ln 1 plus 1 over x over 1 over x. Now x goes to 0 plus, and here I have infinity over infinity indeterminate form, and L'Hopital's rule says that I need to look at the derivatives, limit of 1 over 1 plus 1 over x multiplied by 1 over x prime, derivative of that, divided by 1 over x prime when x goes to 0 plus. I hope that's clear. You remember L'Hopital's rule. Now I can reduce 1 over x prime, both numerator and the denominator. It's a non-zero value. And what will be left? It will be just 1 over 1 plus 1 over x. And when x goes to 0 plus, so this goes to infinity. So 1 over infinity is actually equal to 0. As you can see, my limit is not infinite in this case. It's finite, which means that this is not a vertical asymptote. Not a vertical. So we just found one vertical asymptote here. Now let's look at the second case B, the slant, the oblique asymptote, which is here. All right, it's a slant asymptote. The slant asymptote, I need to look at those two limits. First of all, let me find my slope, which is equal to the limit of f of x over x. My f of x is given here, over x. X and x will reduce each other, the fraction. So I'll just have ln. So it will be just the limit of ln 1 plus 1 over x when x goes to either plus or minus infinity. There are two cases here. X goes to two different directions, and we need to consider that separately. That's very important. But in this case, the outcome will be the same for both either plus or minus infinity. You can easily see when x is going to infinity, so this goes to 1 over infinity is 0, 1 plus 0 is 1, so ln 1 is 0. My a is 0. What does it mean? It means that my slope is 0. That means my line is a horizontal one. It's not a slant asymptote, it's actually a horizontal asymptote in this case, with a 0 slope. Actually, it's a candidate. We didn't find the second limit yet. It may not be defined yet. Let's just, hopefully it's a candidate for the horizontal asymptote. Horizontal asymptote, let's say candidate. Let's say candidate. Now let's find B. B is equal to this limit, so f of x minus ax. A is 0, so this term drops out. It will just limit of f of x of the given function. It's a limit of x by ln 1 plus 1 over x. It's actually very similar to that of the vertical case, except for my x goes to infinity plus minus instead of 0 plus. Here, x goes to plus minus infinity, and the limit is the same. You can see that, yeah? And again, we can resolve it the same way using the L'Hopital's, because right now, when it goes to infinity, it will be 0 by infinity, indeterminate form. And again, L'Hopital's, yeah? L'Hopital's will give me actually the limit of, I will get exactly the same thing here. So I can just write it 1 over 1 plus 1 over x by 1 over x prime over 1 over x prime. X goes to either plus or minus infinity. They reduce the fraction, those 1 over x primes, and I just need to consider that. And in both cases, when my x goes either plus or minus infinity, 1 over infinity goes to 0, so 1 plus 0, 1. So 1 over 1 is just 1. In both cases, it's equal to 1 when x goes either to plus infinity or minus infinity. So it's just 1. Looks like both limits are defined, both limits exist, which means that we do have a slant asymptote, and actually, in this case, it turns out to be a horizontal asymptote. So we have a horizontal asymptote. Y is equal to 1. That is the equation of the horizontal asymptote. Let me just summarize it here. In this example, I have used a calculus approach involving limits to find the equation of the slant asymptote. We also found vertical asymptotes by looking at the domain, and the slant asymptote by looking at those two limits. And what's important, when you consider those limits, be careful when the s goes to either plus or minus infinity. It's a common mistake because you may get different results. We're just lucky. It's a simple case. In both cases, we have the same slope 0, 0, and the same intercept 1 and 1 for both directions, either plus or minus infinity. And my next clip, I will demonstrate a challenging problem, more or less complicated function, when we have different values for the slopes and the intercepts when x goes to either plus or minus infinity. And this is actually a bug in computer software. There are so many software packages, you can just Google them. The graphing calculator packages, the asymptote graphing packages, Wolfram Research and others. You just give a function name and it spits it out the equation of the asymptote. And I just discovered one interesting function for which, if you use it for one of those software packages, it just spits out an equation of only one slant asymptote, and actually that function has two slant asymptotes. That's because the software engineers did not consult us mathematicians properly. They overlooked the domain. They overlooked the domain of that function, and they just considered, let's say, only positive case, and they generated an equation for that case, and they did not generate an equation for another part of the domain. today, as of today, December 11th, it's a small bug in the asymptote graphing packages. As of today, I hope sometime in the future it will be resolved. Thank you very much for your time. I will see you soon in my next clip, part 2, where I demonstrate more examples and this challenging problem for the computer packages. Thank you very much again. Bye-bye.